Hi everybody. I've decided to combine Chapter 7, Section 7.4 and 7.5 because they're kind of brief and kind of related. So Section 7.4 talks about the application of linear systems. And so we've learned that there are three ways that we will solve linear systems: graphing, substitution, or linear combination. So the time when we would choose to use a graphing method to solve is when being approximate is acceptable for your answer. If you just need to be close enough, have a ballpark figure, it's something maybe that you can't really project because you're using two linear models to decide when they would meet. Well, a graphing application would be the best way to look at these. Just the way when we were doing our linear models. It's in a way of, we could use it as a way of extrapolating two different models together. That's kind of a good way to think about it. Substitution would be something that you'd use when your coefficients are small on your variables, often when they're -1 or 1. This is kind of a gimme. If you have either of these very small substitutions, or even if it's only in one equation, you might use substitution as opposed to linear combination. Linear combination is the thing that you use when the coefficients do not cancel out easily, where manipulating the equations is going to get you to a reasonable solution. And now we come to the idea of identifying the number of solutions to a system of equations. And so we've actually already done this when we talked about parallel lines and perpendicular lines. So when two lines intersect on the graph, so if these are both members of a system of equation, the point of intersection is the solution, and there's only one solution, right? Because systems have to share a common point. If we were to have parallel lines, which by definition never cross, there would be no solution to the system. Okay, and then the last one is if they had the same equation, they would be the same line. This would be an infinite number of solutions. Okay, so I wanted to refresh your memory. So how are we going to tell that? Is really when we rewrite the equations first in slope-intercept form. They would have different m's, could be, same b. Okay, no solution would have same slope, and a different b has to have a different b, cannot have the same b. This one could, let me put that back over there. Different b is a must, and an infinite number of solutions is the same m and, oh, you know how I am, don't put the plus sign, and b. Okay? Okay, so now that we talked about how we would tell those things by the equation, let's talk about how we would tell it when we are working with a system of equations and we're going to solve it. Well, the first thing, let's take a look at no solution. So that's when we have a pair of parallel lines, we said. Okay, so how would we know that? Well, the first thing is when we put them into y equals mx plus b form, we will end up with equations that have the same slope and a different b. So we knew that already. We may find this when we are substituting. When we do substitution in an equation, it will produce an error when there is no solution. So when you set up an equation and with substitution and you're solving for the single variable, so I'm just going to use the equation that's in the book, y equals negative 2x plus 1, and the second equation was 2x plus y equals 5. When I substitute in the value of y, and you can see these two x terms are going to cancel each other out, and I end up with an answer 1 equals 5. So when this happens in the middle of my substitution solution for linear equations, then this tells me already that there's no solution because I've already come to a place where there's a false answer. So how do we tell when there are many solutions or an infinite number of solutions? Well, of course, when we write them in y equals mx plus b form, the equations become identical. But what happens if I have a set of equations where I'm instructed to solve by linear combination? And when I do that, and I have, you can notice that the coefficients in each equation for each variable are opposites. So I have a positive 4x minus 2y equals negative 6 in the top, and I have a negative 4x plus a positive 2y equals 6 in the bottom. When I solve this, I end up getting 0 equals 0, which is absolutely a true statement. So when both variables though, are eliminated, that means that I have a pair of parallel, I have the same line, right? When I simplify both of them, if I went back and isolated the variable, I would end up with the same line. The last instance is the situation that we have been working on throughout the chapter, and that is when we use any method for linear systems and we come up with one single point at which they intersect. And so this has exactly one solution. I hope this has opened up for you a few things to keep in mind when you're working. Kind of keeps you from getting all the way to the end and realizing you didn't have to do all that work. We're going to spend some time in class doing actual application practice, so I think that's going to be it for this section.